Okay, here's a word problem. Perfect scenario to use some linear programming. So we have an airline company who is updating its security system. The budget for the new metal detectors is $75,000. The airline has a maximum of 18 security guards. There are two types of detectors available, so we have to find the optimal amount to get of Unit A and Unit B. Unit A costs $5,000. Can process requires one guard and can process 300 people per hour. Unit B costs $7,500, requires two security guards, and can process 500 people per hour. So Unit B has more reliability, better reliability record. It's been mandated that you need to have at least 4 of those types. Determine the number of units each type should be in order to maximize the number of people processed. Alright, so that right there, maximize the total people processed, that is the objective function. Alright, so that's not going to be a limit. We'll put an OF here. And if X is the number of unit A's and B is the amount of A's, and Y is the amount of unit B's you have, X is A, Y is B, then for every unit A you get, that's 300 people processed, and for every unit B you get, that's 500 people processed. So this right here, 300x plus 500y, we'll call it equals P. That's what we're trying to maximize here. And then our constraints are going to be from the other information that we're given. So for the number of guards, it said that for every unit A, that's one guard that you need, so like 1x, and for every unit B that you get, that's 2 guards you need, so 2 times y, and we only have 18 guards available for each shift, so one of our constraints will be x plus 2y has to be less than or equal to 18. Alright, the cost, we only have a budget of $75,000, so we have to make sure that our cost stays under that, $75,000. And for every A that you buy, that's going to cost $5,000. All right, and then for every B unit that you get, that's going to cost $75,000. So that yellow one right there, that's another one of our constraints. All right, and then last are the minimums that we need of each. So there's no constraints for the unit A's. We just have to make sure that we can't buy negative amounts, so we'll say x has to be greater than or equal to 0, but it does say because of the reliability record that we need at least 4 unit B's, so y has to be greater than or equal to 4. Alright, so now I'm going to pause this and graph these on my calculator. Okay, so now I have these inequalities graphed on my calculator. So if we hit tab and look, I have to put these two in point slope form. Alright, if I just show you which one I'm doing, I should probably have this up already. My apologies. Alright, so for these two here, I put them in point slope form. And then for x is greater than 0 and y is greater than or equal to 4. Oops, I actually forgot to do that, so this is a good opportunity to show you. Y is greater than or equal to 4. Alright, so now we have this shaded region. So we have this point right here, which is at 0, 4. So our shaded region has 4 sides. We also have this y-intercept here, which is at 0, 10. We have the intersection of these two lines, so that's 6, 6. And then another point that we have that's a vertex of our shaded region, we could find by doing intersection. So analyze graph intersection and see where this intersects with that, and we see it's at the point 9, 4. So 9, 4, 6, 6, 0, 10, and 0, 4. So those are our 4 vertices of our shaded region. Now, to find the optimal solution, we're going to plug it into the cost function, because that's what that's our objective, trying to maximize the people processed. So when you plug in the 4 points into the different into the same objective function that represents people processed, we maximize the people processed if we get 6 unit A's and 6 unit B's. So our final answer is we want to get 6 A's and 6 B's to process a maximum of 4,800 people.